Hello, good afternoon, everyone. Today is the week sixth of this deep learning IT Ropar course, and this lecture will be recorded and uploaded on YouTube also. So, if students are not watching now, then they can watch it through the NPTEL portal of this course and through the uh, tutorial classes. You will get the spreadsheet. There, you can get the link of all these lectures. So today is the week six. We will discuss some of the important problems that were taught in the week six of this course. So we will start with autoencoders. Like the main topic which was covered in this week was autoencoders. So we'll start with the first question, that is, which of the following is true for an undercomplete autoencoder? First of all, we'll understand what is undercomplete autoencoder. So before that, we will see the block diagram here. In autoencoders, you can see that xi is the input here, h is the hidden layer, and xi hat is the estimate of the input. So in this, when the number of neurons in hidden layer is less than the number of inputs, that is xi, then this is known as undercomplete autoencoders. And now, if the number of neurons in the hidden layer is greater than the number of inputs, then this is the overcomplete autoencoder. In this, the number of neurons in hidden layer are more. Okay. So we will see here autoencoders, why it is used. It is used to help the reduction in the noise in the data through the process of compressing input data, encoding it, and then reconstructing it as an output. Autoencoders allow us to reduce dimensionality and focus only on areas of real value. So it reduces the redundant dimension and we can focus on the area what are required. So this is the definition of autoencoders, and in the undercomplete autoencoders, the number of neurons in the hidden layer will be less than the number of in. So in this first question, what will be the answer? Which of the following is true for an undercomplete autoencoder? It always performs loss-free encoding. That is wrong because it does not give 100% loss-free encoding, and it always captures only few features of input. That is also wrong because it captures most of the important features of input. Dimension of input layer is less than that of the hidden layers. That is not in the case of undercomplete, that is in the case of overcomplete in autoencoder. And dimension of the hidden layer is less than that of the input layer. So option D is the correct option as we have seen. Okay. So if you guys have any doubt, then you can ask in the comment section of YouTube video also. So in the first question, the dimension of the hidden layer is less than that of the input layer is the correct answer for which of the following is true for an undercomplete autoencoder. Okay. Now coming to the second question, that is, consider a scenario where all the inputs to an encoders are real value. Identify all the statements that holds true for the decoder function. In this question, it is given that a scenario where all the inputs to encoders are real values. Okay, so we'll see both the case when the inputs are binary and real, and then we will come back to this question. Okay, so here you can see uh, in this, let's suppose all our inputs are binary, that is 0, 1. Xij is 0, 1. So here you can see these inputs are either 0 or 1. Okay, so these are binary inputs. Now, which of the following function would be most appropriate for the decoder? Just tell me, like this decoder here at the output end, the decoder will decode. So, which will be the following appropriate? Which is the following function will be the most appropriate for the decoder? See, the inputs are binary. So here you can see tan h will take value from -1 to 1. So this is not appropriate. And linear function can take any real value. So this is also not appropriate. This will take any real values. And logistic function takes values from 0 to 1. So for binary inputs, this logistic function is most appropriate function for the decoder. Okay. Logistic as it naturally restricts all the outputs to be between 0 and 1 because logistic function restrict the outputs between 0 to 1. Okay. So here G, this G is our sigmoid function. That is also the logistic function. So now coming to all the option, but this question asks the real value. So we'll see the second case also. Let's suppose now in this input, the xi are real, like 0.25, 0.5, 1.25, 3.5, and 4.5. So these are the real input values in xi. And suppose all our inputs are real in this case. So which of the following function would be most appropriate for the decoder? So the most appropriate function will be which can produce the real output also. So here in tan h, it can produce only from -1 to 1. So for like 4.5 and 5, this is not the appropriate function for the decoder. And the real function, this linear function WH plus C is the most appropriate because it will produce any real values. So, and this logistic also produce from 0 to 1. So, which function is the most appropriate? The linear function. Okay, understood? So, here our decoder will have the linear function. So, we'll see the now options. Tan h function restricts the output space -1 to 1, hence cannot be used to decode. Okay, this is true because this cannot be used to decode. Second option, logistic function cannot be used as the output space will be restricted to 0 to 1. This is also true because logistic function cannot be used because this also restrict the output between 0 to 1. Sigmoid function can be used. This is false because sigmoid also restrict from 0 to 1. So sigmoid cannot be used here in this question also. And the option D, that is linear function, can be used as it produce real values. So option A, B, D are the correct option for this question. Okay. So now we'll move on to the next question. So here you can see the concept of autoencoder in which one side the inputs are binary, in the second part the inputs are real value. So now we will move on to the third question. Which of the following condition ensures that the encoder of a PCA is equivalent to an autoencoder? So in what case the encoder of a PCA is equivalent to autoencoder? So, when the encoder of a linear autoencoder is equivalent to PCA, if we use a linear encoder and a linear decoder, okay? And also, if we are using linear encoder and linear decoder, then the input is real function. So, what loss function we will use? That is a squared error loss function. We use cross entropy loss function for binary inputs, okay? For real inputs, we use the square error loss function. And it also normalizes the inputs to this formula. Okay. So now coming to the option, which of the following condition ensures that encoder of PCA is equivalent to an autoencoder? So h is a linear function. This is correct. G is a linear function. This is correct. Okay. Because here you can see our G should be linear and also H should be linear. And a squared error loss function is used. So all these options are correct. So all of the above option will be the true option for this question. That is option D. Now we will move on to the fourth question. That is based on Jacobian. Jacobian was used in this autoencoder. So we will see this. So in this question, it is asked to compute a Jacobian of ABC with respect to XYZ, given the following: A is equal to X plus Y plus Z, B is equal to Y plus Z, and C is equal to Z. But first of all, where Jacobian was used, Jacobian was used, where it was used in the contractive autoencoders, where we have added one more parameter in contractive autoencoder. Like we have added the following regularization term in the loss function. We have added the regularization term in loss function. So this was our regularization term, that is the Jacobian. Okay. So now here we have to find the Jacobian. So we will see like how to find the Jacobians. So we know that Jacobian of h with respect to x is given as del h1 by del x1 dot 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 del h1 by del xn del h2 by del x2 dot 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 del h2 by del xn. Here it will be x1 only. Dot 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 del h k by del x1 dot 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 del h k by del xn. Okay. So here we have a is equal to x plus y plus z and b is equal to y plus z and c is equal to z. So we will take one empty, we'll add one empty c, then we will solve this question. Yeah, duplicate page. I don't know, it's not moving. So here you can see, so in this we will find del A by ABC are the three vectors. So del A by del X, del A by del Y, del A by del Z, del B by del X, del B by del Y, del B by del Z, also del C by del X, del C by del Y, del C by del Z. Here our A is equal to X plus Y plus Z and B is equal to Y plus Z, C is equal to Z. So when we do this derivative, we will get del A by del X equal to 1, 1, 1. This will be del B by del X, that will be 0 because there is no term of X here. This is 1, this is 1. And this will be again 0 because no term of X and Y. So this will be 0 and this is 1. Now when you will find this determinant, you will get 1 into 1 minus 1. So this is equal to 1 minus 0. So this will be equal to 1. So the correct option is option C, that is 1. So this is the way to find the Jacobian, which is used in the contractive autoencoder. Okay. So now we'll move on to the next question, that is based on the sparse autoencoder. So which of the following is true for sparse autoencoder? Number of neuron in the hidden layer is less than those in the input layer. So is this the correct option? No, this is for the, we have seen, this is not the case for the sparse autoencoder because we have already studied here that this is for the undercomplete autoencoder where the dimension of hidden layer is less than that of the input layer. If dimension is more, then that is over complete autoencoder. So the number of neurons in the hidden layer is more than those in the input layer. That is the case of over complete autoencoder. This is also not true. Ensures that neurons are inactive most of the time. This is the correct option. And ensure the neurons are active most of the time. Actually, option C is correct because it keeps neurons inactive most of the time. Okay. So, like, if you have any doubt, then you can ask in the comment section also in the YouTube because most of the students are not watching the lecture now. Maybe because they have not seen the lecture till now. So, not an issue. But you can comment in the YouTube comment box. There I can reply. So, for this question, it ensures that the neurons are inactive most of the times. Okay. And one more thing. Like what are the regularization parameter is added in this autoencoder, in this sparse autoencoder? Like the regularization parameter in the loss function it is added. So this is L hat theta that is equal to L theta plus omega theta. So here in this omega theta is equal to summation of L is equal to 1 to K rho log rho L hat plus 1 minus rho log 1 minus rho by 1 minus rho L hat. Okay. So this is the regularization parameter added in loss function of the sparse autoencoder. Okay. And we also know that this sparse autoencoders use a sparsity parameters rho. Rho is the sparsity parameters that is typically very small meters. Like this is typically very small, like close to zero. So rho is say close to zero, around let's suppose 0.005. Okay, and it also tries to enforce it tries to keep the constraint rho is equal to rho L hat. So when you see this loss function will be minimum, so we have to just minimize this regularization parameter also. So this will be minimum when the rho L hat is equal to rho. So this gamma theta will be minimum when rho L hat is equal to rho. Okay. So these are the important things in the sparse autoencoders. And here, what will be the L loss function? That is a squared error loss or cross entropy loss, anything. And gamma theta is the sparsity constraint. Okay. And L hat theta will be the summation of L theta, that is the loss function, plus the regularization parameter, that is omega theta. Okay. So now we can move on to the next question. Like this time we will see the now the dimension of this autoencoder. What is the dimension of H, W, Xi? We'll see for everything. So in autoencoders, it encodes the input Xi into a hidden representation H, and it decodes the input again from the hidden representation. So in autoencoder, what happens? Like I am also trying to cover some of the basic concepts so that if you have already seen the lecture, it will be a revision for you, or if you want to see the lecture, hello Venkata. Okay, so I have already covered the five question. Now this is the sixth question. So this is based on the dimension of all the parameters in the autoencoder. So I'm also just covering the basics of the lectures taught in the week six, so that when you see the lecture or you have seen, it will be revision for you. So like in autoencoder, it is a special type of feed forward only network. In this, first the input is encoded, and this video will be also uploaded on YouTube. So if you have missed, you can watch there also. The link will be provided in the spreadsheet on the NPTEL portal. So there you will get the spreadsheet. So input is encoded into a hidden representation, and after that again it decodes the input from this hidden representation, and now the we check how much is the error from the reconstructed input by comparing with the real input. So input is also decoded. into a hidden representation. So in this case, you can see that H is equal to this H is equal to G of WXI plus B. Okay, weight is W is the weight vector and B is the bias. And again now here Xi hat, this will be equal to F of this Xi hat will be also equal to F of W star H plus C. Okay. And also we have seen in the week 6 lecture that this W star H depends on the depends linearly on the X. So now you can see here that we have to calculate the dimension of H, but we will calculate dimension of all these parameters. So the dimension of H is here D cross 1 because H belongs to RD. So the option A is the correct option for question 6. Even you can answer in the chat box if you know these answers. Now here W and W star is the transpose of their dimension will be the transpose. Like if W is our n cross D, then what will be W star? That will be D cross n because uh, it will be not the transpose. I am telling only the dimension will be just exchanged. The number of row and column will be exchanged in the W and W star. So I will just erase this so that it will create confusion. So now we'll see the next question. We'll In this it is asking for the autoencoder. What is the dimension of W star? So now we know that Xi hat that is equal to F W star H plus C. Now H is our, here you can see in this term, I'll just write it little large. So F is W star H plus C. So our H is here D cross 1. Okay. So now what will be the number of column in W star? That is D. Our Xi is n cross 1. So our C will be also n cross 1. Then here what will be the W star dimension? That will be n cross D. Because n cross D multiplied with D cross 1 will produce n cross 1. So this is W cross H. And after summation with C, it will give n cross 1. Okay. So in the next question for the given autoencoder, what is the dimension of W star? That is n cross D. W star is n cross D. Okay. H is our D cross 1. W star is n cross D. That is the option C is the correct option. If you have any doubt, then you can ask in the chat box. And our Xi is n cross 1 and Xi hat is also n cross 1 because that is the estimation of Xi. Okay, so we'll move on to the next question. For the given autoencoder, what is the dimension of B? Now we will see what is H here. H is equal to G of WXI plus B. We have already seen for the decoder part here. We have seen for decoder part what are the dimension of W star, H and C. Now we will see for the encoder part also that is given with the formula H is equal to GWXI plus B. Here our XI is again n cross 1. Okay. So in this question it is asking the dimension of B. And what will be the W? W will be the dimension of W is the transpose of the dimension of W star. So that is in the previous question it was n cross D. So it will be D cross n. Okay. Now what will be the dimension of B? That is D cross 1. And also you can say directly the dimension of B. Like here B is added to all those parameters here. So H is our D cross 1. So B is also equal to D cross 1. Some, yeah, you have answered D cross N for last question, I guess. No, this question. No, no. Because here it is asking dimension of B, not the W. Oh, you are saying the dimension of W is D cross N. Yes, that's correct. Well correct. But in this question, it is asking dimension of B, that is again D cross 1. Okay. So now we'll move on to the next question. So this is like a different question. So before that, we will see one more thing. Like what are the different regularization parameters added to the different encoders, like different kinds of autoencoders. So in the week 6 lecture, this loss function L hat theta that is used. Why we use L hat theta? Why we add regularization parameter so that the model will not overfit. We add regularization parameter to optimize the model so that it will not overfit. So we add regularization parameter so that the model will not overfit. So we have studied various regularization parameters like L2 regularization, that is uh, also known as weight decaying. In this our omega theta that is equal to lambda theta square. Okay, and we have already studied in today's tutorial session, that is sparse autoencoder. In this what we have done, in this our omega theta that is equal to I is equal to 1 to k rho log rho by rho l hat plus 1 minus rho log 1 minus rho by 1 minus rho l hat. Okay, so like I have already taught this today, you can see here. So when will be this regularization parameter will be minimum? When rho l hat is equal to rho. And if this will be minimum, then our L hat theta will be also minimum. So loss function will be minimum. Okay. And in sparse autoencoder, rho is typically very small. It is kept at like 0.002, like that. It is kept near zero only. And we have studied one more regularization parameter, that is contractive autoencoder. In this, we have to calculate the Jacobian also. So omega theta is equal to del hi by del xj square. Okay, so these three are the regularization parameter in these autoencoders we have studied. So now moving to the next question, that is the ninth question. Select the correct option. One way to implement under complete autoencoder is to constrain the number of nodes present in the hidden layer of the neural network. Option B, autoencoders are capable of learning non-linear manifolds, a continuous non-intersecting surface. So we'll see 2 points. Like in the under complete autoencoder, having less number of nodes in hidden layers limits the amount of information that can flow through the network. Okay, if there are less number of neurons in the hidden layers than the input, then it limits the information flow through the hidden layer. Second, autoencoders can be viewed as generalization of PCA, another dimensionality reduction method, which discovers low dimensional hyperplane. Okay, so both the option A and B are correct in this question. Because the first option is only way to implement under complete autoencoder is to constrain the number of nodes present in hidden layers of the neural networks. So if the number of nodes in hidden layer is less than number of input, then it is under complete auto encoder. Okay. Option B, autoencoders are capable of learning non-linear manifolds, a continuous non-intersecting surface. Yes, it is non-linear only, and it is just a generalization of PCA. Here also dimension is reduced, and when it can be equivalent to PCA, this also we have studied here in one of the question. I will show you. Like here, autoencoder is equivalent to PCA if we use linear encoder, linear decoder, and a squared error loss function. Okay, and also the input is normalized to this form. So now we'll move on to the 10th question. This is also select the correct option. Autoencoders are supervised learning techniques. This is wrong option because autoencoders are unsupervised learning techniques. Statement B, autoencoder's output is exactly the same as the input. The explanation for option B is the output of an autoencoder are indeed pretty similar but not exactly same. Because when our x hat, that is the estimate of x, that is like almost same as x, but it is not equal to. That's why we find the loss function that can be either cross entropy or square error loss. So the option B is also wrong because it says that autoencoder's output is exactly the same as the input. It is not same as the input. It is pretty similar but little different than the input. And option A is that autoencoders are a supervised learning technique. This is also wrong because autoencoders are unsupervised learning technique. Supervised learning techniques are those in which it is a labeled input and output is there in the training data set. And in unsupervised learning set, unlabeled data is there in the training data set. So both options are false. Option D is the correct option for this question. So in this week 6, only it was taught about autoencoders. So any doubt, then you guys can ask in the comment box. And some of you have missed the starting part of the lecture, or some of you will see it later. So for that purpose, we are uploading all those videos on YouTube as well. You can watch there. Okay. And also we have not discussed much about the over complete autoencoder. So let's discuss because then it will be clear. Like in over, oh, my pen got discharged. We'll just wait for 1 or 2 minutes. In over complete autoencoder, the dimension of hidden layer is greater than the dimension of X. Okay. So you must be knowing this. And also what we can do uh, like if the number of nodes in the hidden layer is more, then we can directly copy the xi into the hidden layer, and then again we can reconstruct the output exactly same. But this is useless, and we will not do this because this is just a useless. We will just to know the more features. We will not exactly copy the input directly into the hidden layers. Okay, so you can see over complete auto encoder. So in this, let's suppose this is our input layer xi, that's is having 4 nodes. So in over complete autoencoder, how many nodes will be there in the hidden layer? More than four. Let's suppose 6 nodes are there. This is our h and our output node, that is xi. So this is our input layer. This is the hidden layer, and now this is the output layer. W is the weight between the input and hidden layer, and W star is the weight between the hidden layer and the output layer. So in complete autoencoder, dimension of h is greater than dimension of xi. Okay, and in this case, what we can do one more thing. Let's suppose these are the input. So we can directly copy all those input in this hidden layer, and again in the output we can reconstruct it. Then we can get exactly the same output, but this is useless. Okay, so such identity encoding is useless, is not worthy, because it does not tell any of the important characteristics of the data. Okay, so when you do this, so I will tell you one thing, because it does not tells us about the important characteristics of the data. What happened in this? Like let's suppose uh, we have done this, so it will definitely work good with the training data set. Now when you give to the new data, it have not learned the more characteristics of the data, so it will be not able to predict correctly. So in this case, it will not work properly with, not predict properly for the unseen data. Okay, it will definitely work good with the training data that we have already done. Like we have done the trivial encoding, in which we have just kept the same value in the hidden layer and reconstructed in the output layer. But when you give the new data, it will not predict properly because it have not learned any important characteristics of the data while training. Okay, it has not learned from the features or characteristics of the data because we have directly trivially copied all the data. So for today, I guess we have done. So we have seen the undercomplete autoencoders. In this, the dimension of h is less than x, and autoencoders allow us to reduce the dimensionality, and it also helps in reducing the noise, and it also helps us in reducing the dimension. Okay, and in this after that we have seen like for binary inputs. What functions we are using, which functions are the most appropriate for the decoders. So for any real inputs, this linear function is the most appropriate function for the decoder. Okay, because this logistic will have restricts the output between 0 to 1 and tan h will restrict the output between minus 1 to 1. So next when the I'm just revising the summary of this whole class. Next, when the our input is like sorry, sorry, in this question our inputs are binary. So in this, which is the perfect one? The perfect one is this logistic function because it also gives between the output from 0 to 1. Okay, and this gives any real value. So this is also not perfect. This is not appropriate. This is the appropriate because our input is also 0 1 and output is also between 0 to 1. And when the input is real, then this linear function is perfect because it can give any real values. Logistic function will restrict the output from 0 to 1 and tan h will restrict from minus 1 to 1. So this linear function is useful. And autoencoders is equivalent to PCA if we use the linear encoder, linear decoder and a squared error loss function, and we can normalize the input too, as we can see in this question. And we have also seen how to calculate the Jacobian. This is the formula for calculating Jacobian. And we have calculated for one simple example that was x plus y plus z, and c is equal to z. After that, we have seen the regularization parameter added in the sparse encoders and also some questions. And then the dimension in the autoencoder, dimension of various parameters like w, w star, b, h, xi, xi hat. We have seen the dimension of all these parameters. If you have missed the lecture, you can see it again on the YouTube. It will be uploaded. So today we will finish our class here only. Thank you everyone for attending. So we'll meet in the next weekend, that is on the next Saturday, 3 to 4 p.m. Okay, so bye bye. Thank you.